Alrighty, this is going to be our last lesson for BC. The next video is going to be on polar equations of RQ. So after this, we are essentially done with BC, and then we're going to start reviewing. The first four problems are problems involving horizontal tangents and vertical tangents from the previous lesson. I'm not going to do those, but you guys can do that as a warm-up whenever you get this. But whenever we are talking about area in terms of polar equations and polar curves, essentially what we are going to do here is have this little formula, which is based off of the area of a sector. I'm not going to derive it, but in the book they have it so that you could look at that, or you could just Google how this formula works, but this is from area of a sector. All right, so my area is going to be 1/2 from alpha to beta, and it's going to be r squared, so whatever my r value is. In this case, alpha and beta is between, or the difference between alpha and beta is between 0 and 2 pi. Now, that should say not radical, but radial. That's funny. Radial lines. When we are determining radial lines, what we're going to do is sketch the region. In this case, some of the regions will be given to us, so we don't really have to do that. We're going to draw the arbitrary radial line from the pole to the boundary curve. We're going to ask over what interval of values must theta vary in order for the radial line to sweep out the region R, which we'll see and what that means. And then our answer to part 3 determines my limits of integration. Now, part of this is going to be calculator inactive, and then the other part is going to be calculator active. Whenever you are given a calculator inactive problem, you might need to remember these two trig identities right here. So your sine square of x is going to be equal to 1/2 1 minus cosine 2x. Then cosine square of x is going to be 1/2 1 plus cosine of 2x. An easy way to remember this is that because we have cosine is going to be positive. And then the other one, since this is sine and they don't match up, it's going to be negative. That's just an easy way to remember that, hopefully. All right. Now, in addition to this, you are going to be expected to probably know what the polar curves look like. So like number 1 and number 2, I don't give you the polar curve and you're just going to have to sketch it. So for number 1 here, we want to find the area of one petal of r is equal to 2 cosine of 3 theta. Your sketch doesn't need to be pretty as long as you understand what it kind of looks like. We are essentially good. Now this one right here, since we have cosine and this is an odd number, we're going to have 3 petals, with my petal being, one of the petals being across my x-axis, since this is cosine. Then the other 2 is going to look something like that. It's not going to be pretty, but you know, it kind of looks like a fish. All right, so we have this one petal. What we're going to do here is try to figure out, let's say, my zeros, because I really want to look at my zeros here and what they are, because that might be a little bit important for us. So here, whenever we have 2 cosine of 3 theta, I'm going to have 0 is equal to 2 cosine of 3 theta. So 0 is equal to cosine of 3 theta, me divided by 2. So now we want to figure out when cosine is 0. Cosine is 0 whenever we have pi over 2 and 3 pi over 2. Oops. So that means that theta can be pi over 6, and theta could be pi over 2. So let's see what our 0 is. So if theta is 0, then this means that I have 2 cosine of 0. We know that cosine of 0 is going to be 1. So that means that this one right here, this thing right here, at 0, our theta is going to be, or if theta's 0, then r is going to be 2. That's not really important, but I know it does tell me that I'm starting right here, and then at pi over 6, I'm going to be right here. So that's going to be my radial line. So from there to here to here. So if I were to sketch this right here, and I'm going to sketch one petal, I'm probably going to be looking at this area right here because I'm going from 0 to pi over 6. Now, my graph doesn't, it's not really symmetric, but I promise you that this right here is going to be symmetric to each other. Because it is symmetric to each other, what we're going to do is using my formula where we have 1/2, and then my lower limit being 0, and my upper limit being pi over 6 right here, because if I'm going from 0 right here, and then swooping this up right here, if I swoop it up, well, if you get the idea. If I swoop it up from 0 to pi over 6, I'm going to hit all of this right here, this area right here. So from 0 to pi over 6, and then 2 cosine 3 theta squared d theta. Now, remember, that's only this top part right here. If I want the bottom part right here, remember that because it is symmetric, I'm going to multiply by 2. So now, if I do that, that's just going to give me 2 times 1/2, which is just 1. So I'm just left with this integral that I have to figure out by hand. I'm going to rewrite this. All right, so what we're going to do is go ahead and square that. So I'm going to get 0 to pi over 6 of 4 cosine square of 3 theta d theta, which is going to be the same thing as 4, 0 to pi over 6, 1/2, 1 plus cosine 6 theta. Now, the reason why it's 6 theta is because remember that I'm just doubling whatever my inside value is based off of my little formula right here. I am going to go ahead and simplify the 4 and the 1/2 so that I have 2 up front. And then I am going to go ahead and integrate this. So the integral of 1 with respect to theta is just theta. And then I'm going to use a little bit of hue substitution here. That's going to give me 1/6 sine of 6 theta. And this is going to be from 0 to pi over 6. So now I have 2 times, I'm going to go ahead and evaluate my upper limit. That's going to be pi over 6 plus 1/2 times sine of 6 times pi over 6, which means that this is sine of pi. And sine of pi is 0, so I have pi over 6 plus 0, minus my lower limit, which is just going to be 0, plus sine of 0, again, this is going to be 0, which means that my area here is just going to be pi over 3. So this is the area of one petal, meaning that I'm including this little region right here at the bottom. So it's this petal right here. Assuming that, of course, all of these are symmetric, because my drawing, obviously, it was horrible. Not pretty. But if I were to ask you to find the area of the polar graph right here, I would just multiply my answer, pi over 3 by 3, since there's 3 petals, and then call it a day. All right, number 3. We want to find the area of 2 plus 2 cosine of theta. So what I'm going to do here is figure out my zeros. So that's going to be 0 is equal to 2 plus 2 cosine of theta. Negative 2 is equal to 2 cosine of theta. Negative 1 is equal to cosine of theta. Now we got to think, when is cosine of theta equal to negative 1? And that only happens whenever theta is pi. So we're going to start here at theta is equal to 0. And then we're going to move here whenever theta is pi, so that it is 0. You'll notice that that area is going to be this right here, and it's the upper area. You could tell that this right here is going to be symmetric, so once again, just like number 1, whenever we are doing this right here, I'm going to have my formula of 1/2. My lower limit is going to be 0, and then my upper limit is going to be pi right here of 2 plus 2 cosine of theta d theta. Because I want to find the area of the whole curve right here, and because this is symmetric, I'm going to multiply by 2. And since I'm multiplying by 2, 2 times 1/2 is just going to be 1. So now I'm just going to evaluate what this is. Of course, I forgot to square this. Square. So if I do that, I'm going to get 4 plus 4 cosine of theta plus 4 cosine square of theta d theta. I'm going to factor out a 4 just so that life is simpler. 1 plus cosine of theta plus cosine square of theta d theta. I'm also going to go ahead and simplify this by using my reduction identity. So now I have 0 plus from 4 integral from 0 to pi, 1 plus cosine of theta plus 1/2, 1 plus cosine 2 theta d theta. I'm going to simplify the 1/2. So now that's 1/2 plus 1/2 cosine of 2 theta. Now I'm just going to clean everything up. So where did that 1 come from? Oh, I forgot to erase that. That's why. No, that's 1/2. I'm going to simplify the 1 and the 1/2 so that it is 3/2, so 3/2. And now I am ready to integrate this. I know, crazy. I'm going to do that. All right. So that is going to, okay. So now that's going to give me 3/2 theta plus sine of theta plus 1/4 sine of 2 theta, and my bounds being from 0 to pi. So now I have 4 and then 3/2 pi plus sine of pi, which is going to be 0, which means that sine of 2 pi is also going to be 0. So that doesn't really matter. 0 here, that's just going to be 0. This is also going to be 0, and this is also going to be 0. So technically, the only thing that I really have is 4 times 3/2 pi, which is eventually going to be 6 pi right here. So our answer for number 3 is 6 pi. All right, number 4. You'll notice that for number 4 that we do have symmetry across the y-axis right here. However, I'm not going to do it that way. I'm going to show you that if you don't want to use symmetry, then technically you can still go from 0 to 2 pi. So this one right here, I'm not going to be using symmetry, but you can. You're going to get the same answer. But here, I am going to go from 0 to 2 pi, or 2 minus sine of theta square d theta. All right, simplify that. That's going to give me 4 minus 2 sine theta plus sine square of theta d theta. I'm going to simplify the sine square of theta to be 1 minus cosine of 2 theta. I'm going to simplify this again right here. So now I have 1/2, 0 to 2 theta, 4 minus 2 sine of theta, plus 1/2 minus 1/2 cosine of 2 theta d theta. Now I'm going to simplify the 4 and the 1/2 right here. So that's going to give me 9/2. And then once I do that, I can finally try to integrate this. Okay, so now I have 1/2 of 9 over 2 theta minus 2 cosine of theta, but because I'm taking the integral of sine, I want it to be negative, so this is going to be positive, minus 1/4 sine of 2 theta, using good old U substitution right there. Bounds are from 0 to 2 pi, and then I'm just going to evaluate this. Plugging in 2 pi right here, that's going to give me 9 pi. Cosine of 2 pi is going to be 1, so this is going to give me 2. Sine of 4 pi is going to be 0. So that's my upper bound. Using my lower bound now, I'm going to have 9 over 2 times 0, so 0. Once again, 2 cosine of 0 is just going to be 2. And then 1/4 sine of 0 is just going to be 0. So I have that. The 2's will cancel out, so I'm just left with 9 pi over 2. All right, I think I'm going to split this video up into 2 parts. So what I'm actually going to do here is go ahead and show you the symmetry way for number 4. Because either way, you kind of want to use symmetry or not. I don't care in terms of these problems. The AP exam, sometimes they might ask you to set up the integral, and if they do that, and if it was an MCQ, then you'll probably see something like this right here. Okay, so right here, we got to figure out what this is right here, and that's just going to be negative pi over 2. And then this right here is going to be pi over 2. All right, so I have 2, because I have the left side and the right side being symmetrical to each other. I have 1/2 times the integral from negative pi over 2 to pi over 2. And this is going to be 2 minus sine theta squared d theta. This is just going to be 1, so now I have the integral from negative pi over 2 to pi over 2 of this lovely thing right here again. The reason why I didn't like to use symmetry for this one is because we have a negative right here, negative pi over 2. I mean, you could still do it, but it's just not fun. But, you know, it is what it is. I'm gonna go ahead and just copy what I have right here from the previous thing. And then we're gonna integrate this from negative pi over 2 to pi over 2. Okay, so if I do that, I'm gonna get 9 over 2 and then times pi over 2. Plus 2 cosine of pi over 2. So if I'm thinking about pi over 2 right here, that's going to be 0. And then I have minus 1/4 sine of, let's see, 2 times pi over 2 is pi. And if I'm thinking about sine of pi, that is going to be 0. So now I'm just left with 9 over 2 times pi over 2 for my first part. And then I have my lower bound that I'm going to evaluate. Okay, so 9 over 2 times negative pi over 2. 2 cosine of negative pi over 2, which is down here, which is just going to be 0. And then this right here also, right here, sine of negative pi is going to be 0. So now I'm left with this right here. So this is going to give us 9 pi over 4 plus 9 pi over 4, which is equal to 18 pi over 4, which, once again, we get 9 pi over 2. Of course, this one was a little bit shorter because I used a shortcut of the integral that we did earlier. So either way, if you want to do it using negative pi over 2 to pi over 2, or if you want to use it from 0 to pi here, you are fine to do so. All right, in the next video, we are going to be talking about area between two curves and area shared by two curves. So that's going to be a little extension to top minus bottom and right minus left that we did back in AB. And that's going to be the next video.